So we want to talk about gravitational fields. In your syllabus, there will be 3 fields. One is gravitational field. One will be electric field. The other one will be magnetic field. So what's the definition of a gravitational field? You can see here, a region where a gravitational force is experienced by a mass. So that means, how do you know that you are in a gravitational field? It's when you suddenly wake up in the morning, then you feel heavy because you have a weight. That means you are in the Earth's gravitational field. But one day you wake up, then you feel yourself floating. Then that means you are no longer in Earth's gravitational field. Okay. So, but why would gravitational fields exist? It's because of what Newton said. Remember his famous story about the apple falling on his head one? And all those, right? So he came up with Newton's law of gravitation. So he says that every mass in this universe will attract every other mass with a force which is directly proportional to the product of the masses. That means you must multiply the 2 masses together. The bigger the value, the bigger the force. And inversely proportional to the square of the distance apart. That means the further apart they are, the weaker the force. So inversely proportional to distance squared. So by combining these 2 equations, you get F is proportional to m1, m2 over r squared. You put a constant, because you want to change from proportional to equal, your constant is capital G, which is universal gravitational constant, which is the same anywhere in this universe, and is given by this formula. So look at this constant, is it big or small? 6.67 times 10 to the power negative 11. Extremely small, right? So extremely small, it means that in order for the force to be significantly huge, in order you can feel it, at least one of the mass has to be very, very big. Example, right? Now, if you say every mass attracts every other mass, so do you feel any attractive force with the person next to you? No, okay. Repel some more. Okay, now according to Newton, you cannot repel one, or attract. No matter how much you hate that person, you must still be attracted to that person. Okay, example why we don't feel the force. So let's take the mass between 2 volunteers here. So who wants to volunteer for this calculation? Okay, let's volunteer Cass. And her weight, her mass, according to my calculation, should be around 48 kg lah. Okay, but we round it off to 60 lah. Okay, we put 50 lah, easier to count lah, 50 lah, save a bit lah. Then next to her, Mian Ying, I think about there also lah, let's say 50 lah. After you say, I say one person fatter, the other one thinner. So like that fair lah, both 50 kg. And let's say your distance between the both of you all. Now we must take center of mass to center of mass. Because for these formulas, we are taking for point masses. Point masses means you must assume the entire mass is concentrated at the point in the center. So let's assume that your center of mass is your belly button. Can somebody take a ruler and measure the distance between the 2 belly buttons? Okay. So let's assume it's 1 meter lah, 1 meter. Now, can somebody calculate the force between them, the attractive force between them? Do I have to really measure using a ruler? Let's estimate, okay? So, can you calculate the force quickly? What do you get?
1.667 10 power of
negative 7. So can you see the force is so small? Therefore, you cannot feel it. So in order for this force to be felt, you need to have one of you must be very huge. For example, right, if you are talking about between the Earth and you, but you cannot even say like elephant or whale and all that. So mass is still not big enough. All right, you must talk about like planets, like the Earth and you. Then you will feel the force. So because the Earth's mass, can you guess what's the Earth's mass? It's about 6 times 10 to the power 24 kg. Yeah, so because the Earth's mass is so big, so between you and the Earth, you will feel the force. That is your weight that you feel. Understand? So this is how you calculate the gravitational force. And so it also means that if you put on weight, let's say after Chinese New Year, you actually put on weight, and then actually your girlfriend also put on weight, then the girlfriend always like to ask her, do you think I'm fat? So what should you say? You must not lie. So you must say, don't worry, you are more attractive to me. Which is true, because the bigger the mass, the more attractive the person is, right? Okay, so that way you won't be lying, and you will also make her happy. Okay? So next part is we will learn how to draw gravitational field lines. Now to draw gravitational field lines, you must follow a sign convention. Because otherwise everybody draw their own pattern, then nobody will know what it represents. So they follow a particular sign convention, and the good news is it is similar to the sign convention you used for electric field in your AS. Remember how we draw the electric field for a charge. For example, this is positive charge. We draw the electric fields outwards, right? Negative charge, we draw the electric fields inwards, right? Do you know why? What sign convention did we use to draw electric field? We used the force acting on a positive test charge. So direction of the field lines follow the direction of force acting on a positive test charge placed in the field. Example, if you want to draw the field of this positive charge, you put positive test charge everywhere. All these positive test charge will be repelled or attracted to the positive charge. So all the forces will be outwards, right? That's why all the lines are outwards. If you want to draw the electric field for a negative charge, you put positive test charge everywhere, you'll be attracted or repelled. Attracted. That's why the lines are inwards. Okay? Now, for gravitational field, we use a test mass. That means if I wanted to draw the gravitational field for this mass, I put test mass everywhere. Now, didn't Newton say that this test mass will always be attracted? So the test mass attracted, so the force inwards, so all your field lines are inwards. Do you understand? So for gravitational fields, they're always inwards towards the mass one. It's never outwards one. Why? Because the force on any test mass is always attractive. Whereas for electric field, the forces can be repulsive or attractive. That's why you got going out and inwards also. You see the difference here? And as in all field theory, the closer the lines are, the stronger the field. The further apart, the weaker the field. That means near the surface of the mass, the force is the strongest. Further away, the field is weaker, so the force is also the weakest. Do you understand that? Okay, now let's talk about gravitational field strength. So it means how strong the field is. So gravitational field strength is given by the formula F divided by m. So the definition is force per unit mass. But it's not something really completely new to you, because in electric field strength in your AS, remember you use F divided by Q?
Yes.
Which is force per unit positive charge?
Yes.
So now is for gravitational field strength is force per unit mass. And if you take the force, which is, can you remember the formula for force? G m over r squared. If you divide by 1 m, the 1 of the m will cancel, right? So you will end up with Gm over r squared. So these are your two formulas for your field strength. Let me write nicely. So these are your two formulas for your field strength. This and this. So what is the difference then? Now, unit-wise, no problem. Both will give you the same unit, which is Newton per kg. That is field strength. And but do you know what's the difference? Not the m. This is 1 m, this is 1 m. So it is very important to be able to know what m to substitute whenever you use this equation. Which m does it represent? Use this equation, which m does it represent? What do you think? If I use this m, what does it represent? So give you an example. Let's say this is the Earth. This is the center of the Earth. And you know the Earth has a gravitational field, right? So to find the gravitational field strength of the Earth at point A, so let's say I put a let's say I put a test mass here. Okay, I put a test mass here to find the field strength of the Earth at point A. And if I use this formula, what does the F represent? The force acting on the test mass. But what does the M here represent? The mass of the Earth or the mass of the test mass? Okay, what about if I use this formula? What does the M here represent? Mass of the Earth, correct. So actually, the shortcut to remember, how to remember is, if the M is at the bottom, that means if you look at the formula and there's only one M, and the M is at the bottom, is the less important mass, it must be the test mass. But you see there's only one mass and the mass is on top, it must be the more important mass, is the mass that produces the field. I prove to you, in this room here, all of us have different weight, right? That means we have different force, correct or not? But is the field strength in this room same or not? Same, where you are sitting, where every one of you are sitting on your chair, is the field strength there the same? What's the field strength at the surface of the earth? All same, right? So how can you get the same? I'll give you an example. Now, the force on each of us are different. For example, small mass like me will have small force. Big mass like Alex, let's say, will have a big force. So what will happen is a big force divided by big mass will get the same answer as a small force divided by a small mass. Understand? So you get the same. So this must represent a test mass because this will increase with the mass. So this must be a test mass. But if you use this formula, what does the R represent? It represents R represents the distance from the center of the earth to this room. And that is fixed. So the M must represent the mass of the earth because the field strength at this point is constant as well. So this is constant, this is constant, this is constant. So your M also must be constant, which is the mass of the earth, not us. Understand or not? So force will vary with the mass. Different masses like us will have different force. But we will all have the same field strength because the field strength is nothing to do with us, it's the field strength of the earth. So the field strength of the earth at this point where we're all sitting is all the same. They are all the same because we are in the field strength of the earth. You understand? Okay, so that is the concept between force and field strength.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.